You're being cued. All right. Hi, everyone. So it's a pleasure to introduce Chinmay. So Chinmay is a researcher at IBM Quantum. He just recently finished his PhD at UC Berkeley with Umesh Vazirani just last year. And even before that, he was an undergrad at Caltech. Actually, that's where we met when I started my PhD. And since then, he's gone on to do some of the deepest work in quantum complexity theory that touches upon quantum error correcting codes, entanglement, quantum many-body systems. And this work has led recently to the breakthrough resolution of what is known as the NLTS conjecture, which he'll tell us about. And this has generated a lot of buzz in our community. So very excited to have Chinmay. Take it away.
Thank you. Okay, yeah, it's a real pleasure to be here. You can hear me? Everything good? Okay. Yeah, so I'll be talking mostly about, as Andrea said, this resolution of this conjecture, which is this first result here. But then I'd like to, near the end of the talk, just very, very briefly, so when I pull up result 2 at like 45 minutes in, don't get worried. I'll talk very briefly about these and sort of say like maybe a broader perspective on complexity of states in general. Okay. So maybe we should start by saying, this talk is going to be on many things, but the core idea is going to be about how to classically describe quantum states or quantum systems. There'll be a fundamental tool which we'll use to understand this, which is quantum computation. I'll show a little bit about how computation gives a very nice, clean perspective with which you can understand complexity of quantum states, whether that be a state that you might build on a quantum computer itself, or a state which you might interact with in a physical perspective. As a consequence, this talk will touch on a subject in physics called condensed matter, which is studying the physical properties of matter. And we'll try to argue about how certain properties of physics can be defined very clearly through this quantum computational lens. And this talk will be a little bit about entanglement at warm temperatures and whether that's a feasible thing, whether you can theoretically have entanglement at like 1 Kelvin or something like this. And the mathematical tool with which we'll use to sort of make that rigorous is a notion of circuit lower bounds from complexity theory. Okay, so to start off, if I'm going to make any statement about the description complexity of quantum states, I should say a little bit about why quantum states are complex. And you might have heard that quantum states are exponentially complex. And a simple way to think about that is by thinking about sort of the simplest quantum system that people write down, which is this notion of a Bell pair, or the EPR pair. And so what this is really just two coins. You can think of them as either being heads or tails. But they are entangled, which means that their description cannot be defined by just describing one of them at a time. So the way to think about that fundamentally is that each coin by itself looks like randomness. Half the time it's up, half the time it's down. But it is fundamentally correlated with the other coin. Whenever this one's up, the other one is also up. And whenever this one's down, the other one's also down. And this, in fact, is not a property just of the standard basis. If you're familiar, it's sort of this property in all bases that they have this correlation. But what that says is that, describing the state of this system, it doesn't suffice to say this is two coins, both that are 50-50, because that misses the whole point that there's some fundamental correlation between the two of them. Contrast that with the system on the right, a classical system, which is, one coin's in tail and the other one's in heads, and you could always describe that as a sum of the descriptions of the local parts. Right? So what this suggests is that quantum entanglement at its core, if you take one thing away from this, is quantum entanglement exists when it doesn't suffice to describe each individual particle. Right? That's like the core thing that makes describing a quantum system complex, is that you can't break up the description into a sum of small little parts. Generalize that to an n-particle system, and the postulates of quantum mechanics say that, okay, the best way to describe this system, or I should say not the best way, but a definitive way to describe this system, is by a really tall vector. A vector of exponential size, the 2 to the n size vector. And this vector is a vector of norm 1, and it describes all the possible interactions between the particles. Okay, but this yields sort of a fundamental problem, which is that the space of n particle states, the space in which you could, the description complexity describing these systems is insanely large. Even if n was like 500, describing 500 particles would require writing this 2 to the n sized, vector, and that seems sort of infeasible. So maybe it's just the case that describing 500 particle systems cannot be fundamentally done. So this was a question that Feynman thought about, and one of the seminal references a lot of people make is he says, okay, well then the only way to sort of simulate n particles is with a quantum computer. A lot of people take this, like Feynman gave this talk at Caltech in the 20th century about this. But actually that talk, he said something a little bit more. He said, well, either that's the case, or there's something wrong with this picture, that although there is this exponential size vector that describes the system, perhaps there's a considerably simpler description. So perhaps we can actually describe the system via a much shorter description that doesn't look anything like this vector. And this is sort of a way to think about, well, how is it even possible to represent quantum states without exponential complexity? And the answer you might get is that in reality, there exists a physically relevant corner of this large space in which all the quantum states that we are interested in studying lie. So perhaps it's the case that the full generality of quantum mechanics requires these very large vectors and it's impossible to describe. But it's seemingly possible that the states that are of interest from some physical perspective lie in a much, much smaller corner, and that corner is tractable in this sense. So what does this physically relevant corner look like? Well, to understand that, we need to understand what are the sort of systems that occur in physics. And I'm going to be a little bit general here, and a little bit imprecise, but all of this can be made with higher granularity of correctness. So we can imagine an array of particles. Here it's drawn 2D, but it could be in any dimension. And we imagine that these particles are governed by some interaction setting, and these interactions are somewhat local. So particles only interact sort of with their neighbors. Interactions do not occur between particles that are on one side and the other of this grid. So you have interactions, and they could be horizontal or vertical in this 2D grid, and the whole system is defined by this collection of local interactions. And how do you describe each local interaction? Well, it's not very complicated. Each local interaction is described by a Hamiltonian, which is just a small matrix. So if K is, say, 2, it's a 2 local interaction, then this Hamiltonian is just a 4x4 matrix. And if these two particles were in isolation, then the evolution of these particles would be described by the Schrödinger equation of this Hamiltonian matrix. But the problem is that these two particles are not in isolation. We're considering how they behave in this grand system. So what you get is that, here's an example. Like, here's a Hamiltonian that prefers the states being 0, 0, 1, 1. This is a very physically relevant example. This is, say, an example where you pin down two magnets so they can rotate, but they can't physically move. And what you'll get is that the magnets will line up both pointing north in one direction, or they're both point south in the other direction. So both of those are the favorable sort of solutions, and that could be sort of a physical interaction you see. And this Hamiltonian has a simple matrix. Maybe I should say another example, which is, well, imagine that Bell pair that I said on the first slide. You could write down a Hamiltonian where the low energy system prefers to sit in that Bell interaction. And that, also has a similar matrix. So given this sort of system, it's all about taking these local interactions and trying to understand how they fit globally. Okay, so let's add a little bit more mathematical precision just so this makes a little bit more sense. So even though this interaction can be defined as a very small matrix locally, you can always observe any interaction and think of it as an action on all the particles. And this is described by just taking the tensor product. So I can always think of this interaction not just as defining this local picture, but now what I want to understand in the global perspective is a very simple mathematical formulation as to how that extends. So then the name of the game is that I have a bunch of interactions. I have interactions between all the particles, And those whole interactions are defined by a matrix. And what matrix is, it's not a very complicated one. It's just a sum of the local interactions extended out. So what we get is that the whole interaction space is defined by this really large 2 to the n by 2 to the n matrix with some special structure. Okay. So, this Hamiltonian for physically interesting systems has a short polynomial description. It's not a general 2 to the n by 2 to the n matrix. It's actually some very small specific subset of those matrices. So it stands to reason that the states that sort of correspond to this Hamiltonian might also have a shorter description, right? Because certainly the Hamiltonian itself does. And what are the interesting states? Well, from physics, you'll get that the relevant states, well, a subset of the relevant states that you might be interested in understanding are what are called the low energy states of this Hamiltonian. This is sort of what the system thermalizes to, if you're familiar with that terminology. And what does that mean? Well, the energy of a state is not a complicated notion. It's just an eigenvalue. And it's an eigenvalue with respect to this Hamiltonian matrix. So the states of interest are what are just formally just the low eigenvalue states of this matrix. And low energy just means small eigenvalue. The only problem is that calculating the low energy states of a Hamiltonian is sort of a tricky thing. It's not easy to necessarily do, because now you have this problem that these interactions between the particles may not play nicely, right? In the case that the interactions were, say, defined by the magnets, the first example, you would get a very simple solution. Everything would point north or everything would point south. And those are the two stable solutions. But what happens when the interaction is something more complicated, like the quantum example for the Bell pair? It's not a priori clear how you might combine all those interactions to get a global solution. Okay, we'll come back to this in a second. But suffice to say, this idea of a physically relevant corner, maybe we should just simplify this and say, what we're really interested in understanding is the low energy states of local Hamiltonians. And let me, yeah.
Sounds like there are two things you're talking about. One is the description length, which is small for what you described, versus calculating what they are, which is a separate issue. Is that right?
Yeah, that's a great point, right? As Anup, I think, is suggesting, why don't I just describe the low energy or even the zeroth energy state as just, it is the zeroth energy state of H. And that's a great exact answer, but it's also a totally useless answer. It's useless in a very formal sense that you can't really do anything with it. Like a polynomial time machine would sort of give up. It was just given that description. So sort of, we need to hit some sort of tangible notion of a useful description. And we'll touch a little bit on that in a second. Yeah. Okay, so maybe I should say a little bit about what I mean by low, because I sort of left that term vague. Well, there's two versions. One is sort of the ground state, which is the eigenvector of minimal eigenvalue. This turns out to be the quantum analog of sort of satisfying solutions. So if you're familiar with like constraint satisfaction problems, this is just the quantum analog. It's this thing that satisfies everything. And the second thing is the states of up to energy epsilon n for some constant epsilon. And this is just the eigenvectors which have small realized eigenvalue. And this definition of low is actually of physical interest because this describes the set of states of constant temperature. So as n grows to a thermodynamic limit, as n starts to describe a whole system, what you get is that the eigenvectors of eigenvalue less than epsilon n are also fundamentally describing those low energy systems. So this is sort of what the system turns to when you experience it at low temperature. Okay. So we have that this Hamiltonian has a short polynomial length description. But then you should ask, okay, what I wasn't interested in was this physical system itself. It wasn't like the rules of the game, but it was actually the solutions or even the approximate solutions of the game. How hard are those to describe? And this is where Anup's question comes in. Yeah, there is that description, but it's a totally useless one. So there was a proof by Kitaev that showed that it's actually quantum NP hard to exactly describe the ground states or the exact solutions to Hamiltonians. So we don't see any hope in being able to describe in any useful manner the ground states of Hamiltonians, unless we're breaking some huge notions in complexity theory. So you might ask, what are the low energy states? What about the approximations? how hard are those to describe? And the goal of today's talk is to try to convince you that's probably not the case. That even describing the low energy states, the states of energy less than epsilon n, should be hard in general. Formally, what we are going to try to do is we're going to try to write down Hamiltonian systems, like physically realizable. We're going to write down what those interactions would look like, so that all the low energy states of those Hamiltonians do not have some notion of classical description. And we mean a useful classical description. Okay. Yeah, question?
Maximum possible eigenvalue of the Hamiltonian?
It's n. So let's say there's n different terms in the Hamiltonian, then the total eigenvalues, the scales say 0 to n. Yeah. Okay. So why study description length? I mean, it's a reasonable question. Like, what does description length give you? Why do we care about if it's a short description, long description? Well, it comes from this idea that there's sort of this fundamental connection, this like nascent connection between description length and entanglement structure. And this is something that I brought up on the first slide. That what it really means to be quantum entangled is that it doesn't suffice to describe each particle individually, which means that the description has to be longer than describing each of the particles one at a time. Right? And this suggests sort of this notion that the longer the description of a state, the more complex the entanglement underlying. And so this tells you that description length is sort of some measure of entanglement complexity. It's not exact in any formal sense here, but this is sort of a notion that you should hold in your head. Yeah.
So is it cheating to say the description is I'm going to apply this Hamiltonian, which has a short description, n times?
Yeah, because that again is a totally useless description. It doesn't help you with any idea, right? It would totally, applying it many, many times would sort of get you there, but it's not something that's computationally tractable, right? And we can say a little bit more about what it means to be a description, in a useful description in just a second, right? Great question. So, yeah, our central question may be rephrased, and this idea is, are there local Hamiltonians with no short descriptions of their low energy states? Okay, so what we need, though, is somehow to bring in this question of usefulness. And a good way to think about usefulness is through a notion of computational complexity. And we're going to sort of say that there's a relationship between entanglement structure and computational complexity that will help us sort of understand this. And this connection between entanglement structure and computational complexity has actually been quite useful in many other areas. It's been useful in notions of physics, of topological order, or conjectures about gravity and such. Okay, but to say that, let me say one word on quantum computation, which is quantum computation is really just about futuristic computers which are built from qubits instead of bits. So they're built from the core of quantum mechanics instead of classical mechanics. And there's been many use cases of quantum computation, such as simulating physics, improved algorithms for certain problems, such as factoring, and novel cryptographic schemes. The one I would like to focus on is simulating quantum physics. So quantum mechanics and quantum computation gives us a very nice picture with which we can understand quantum states. And let me say a little bit more about that. So to do that, I'll have to say a little bit about the circuit model and computation. So, you can always say that computation is defined as like, you start off with some inputs, all zeros on the left, and there's some computation. You apply a gate, such as a bit flip gate, and, you get out an output. And, you can do more complicated things like add controlled bit flips and such, and you have computation. And then you can even say something more, that computation is viewed as like an input-output function. Meaning, you change the input, and then you have different outputs. So your computation is this notion of input-output. And the same can be done of quantum computation. You can always describe it in this circuit model, where you start off with some quantum state, and you let it evolve. Of course, if you run a classical circuit like the one here, the output you get is only a classical state. It doesn't suddenly do something interesting. But then you can add a gate which is not diagonal, like the previous gates were, and you suddenly get that quantum computation, even though it starts off with classical inputs, unentangled inputs, the result is some entangled state, which can only be described quantum mechanically. Okay, so what does that tell you? Well, it says, okay, it says two things. One, you can also view quantum computation in this input-output model, but it's saying something a little bit more, which is that it gives you a measure of complexity for states. And this is a fundamental, interesting notion that it says, hey, not only is this model, describing some way of manipulating information, but it's also giving me a sort of recipes for constructing quantum states. And now that I look at it this way, I can do something interesting, which is I could say, well, what is the minimum depth, where depth is sort of the number of non-trivial operations you have to do in series to generate any given quantum state? And that sort of measures the complexity. And the intuition should be that, as description length gets longer, we think of that as more complex entanglement. And this is sort of a similar notion, right? As the circuit depth goes longer and longer, it's seemingly that we have to do something more and more to build this kind of complex entanglement. And that intuition turns out to be correct. And you can actually say something rigorous, which is that we can sort of use depth of a state as sort of a yardstick with which we can measure complexity of quantum states. So what we have is actually three interesting regimes. One regime of sort of trivial depth. Whenever you have a quantum circuit that's very short. So it's a circuit on n qubits, but its depth scales like log n. And what turns out is this trivial regime is sort of trivial because there's an efficient classical algorithm for calculating the energy of the state for any local Hamiltonian H. So this turns out to be that if you're given such a short description, it turns out to be a very useful description. And it's a useful description for a specific type of computer, that just being a classical computer. So a classical computer can say, hey, if you tell me a quantum state of trivial depth, then I can tell you anything you want about it, effectively. I can tell you all the physical properties that you might be interested in. So these really short circuits, describe states that are morally classical. But then, if you go a little deeper, you get that, not only is there no longer might be a classical algorithm for calculating the energy, but there's a quantum algorithm. So if you're describing a state which requires polynomial depth, then what you get is that there's a quantum algorithm for calculating the energy of the state with respect to any local Hamiltonian. And then you could go even further, and what you get is that all states can be described by quantum circuits up to some depth, up to some exponential depth. So what we see here is that, again, we see this notion that there's this small space, this small physically relevant corner that we're able to access. Most states require exponential depth to generate, but of the states, there's a small set that we can access using either polynomial depth circuits with our quantum computer, or we can sort of understand with our classical computer that are very, very short depth. Yeah? Exactly. No, the efficient quantum algorithm is of polynomial size.
But the state itself is generated potentially with exponential size number of gates.
No. Okay, so that's a great question. So the rules of quantum mechanics don't allow gates of arbitrary fan-in because they aren't reversible. So the gates that we will consider for the purpose of this talk have only a fixed amount of fan-in. So having polynomial depth also implies polynomial size. Okay, sorry, yeah.
And one more question. How does this correspond to Feynman's idea of the space of realizable? Does this yardstick correspond to the space of interesting Hamiltonians that?
Right. So in some sense, you might ask, okay, for all the interesting Hamiltonians that I write down, are all the solutions, can they be described by polynomial depth circuits? And that's actually a fundamental question that we don't know the answer to. And I have a result showing that in some oracle model, that's actually false. That even quantum computers, these polynomial depth circuits, cannot describe the solutions. But that's in an oracle model, not an unconditional statement. And I'll say a little bit about that around 50 minutes in. So, yeah. Great question. Okay, so what you get is sort of this notion that there's sort of three regimes, right? There's classical, tractable quantum, and intractable quantum. And this yardstick is sort of giving a very nice measure of complexity. And it was doing what we wanted from description length, but it's also adding this notion of usefulness. Now, I should say that this is not the only notion of usefulness plus description complexity. There are other ones one could write down, but this is at least a certain great one to start off with, a necessary but maybe not sufficient condition. So our motivating question was, are there local Hamiltonians with no short descriptions for the low energy states? But it's kind of hard to say something about what short description meant. So using this computational perspective, we can ask another question, which is, are there local Hamiltonians with no trivial depth low energy states? And the reason trivial depth is coming up is because the trivial depth states were sort of the classical states. So we're asking, are there Hamiltonians for which the solutions and the approximate solutions are fundamentally quantum? They're fundamentally quantum in the sense that this simple measure of complexity sort of declares them as quantum and not classical. Okay, it's a reasonable question because we sort of want to understand how does quantum mechanics behave in this robust, sort of warm regime. And in fact, this isn't an original question of mine. This was actually a famous conjecture called the NLTS conjecture by Friedman and Hastings, who asked this in 2014. And they asked, can I write down some n-qubit Hamiltonian system for any n with the property that every low energy state requires at least omega of log n circuit depth. And the omega of log n is just tossing you out of that trivial depth regime. Yeah, Rahul?
I have a question on the previous slide. So if you have a quantum state with, let's say, the classical, but that does not necessarily mean you can still efficiently compute it, right? You could have a quantum state where the description is hard to compute, but the circuit depth is still log n.
Sure, absolutely. But you can verify that it is a solution shortly. So yeah, so that's a great question. What does useful mean? In this sense, we're formally meaning that useful means sort of verifiable. You can verify that it's a correct solution. Great question. Okay, so this was a conjecture, and there was a ton of work in the interim to try to work at it. Some of it my own. And what each of these works did was they tried to prove circuit lower bounds on the complexity of states. So that was the real goal. So now that we took this in a problem, we sort of converted it into some mathematical problem which we now can access tangibly, which is to prove circuit complexity lower bounds for each of the steps, for each of the low energy states. The only problem was that we didn't really have any idea on how to prove circuit depth lower bounds for all the low energy states. In fact, all the results sort of eluded us. They proved it for sort of specific subclasses of states. And none of the results, got us to proving the circuit lower bounds for all states. Okay. In fact, there was actually some other works that showed that certain Hamiltonians had very good approximations by low depth states, even depth 1 states. So it was sort of unclear as to whether this conjecture was true or false. It sort of could have gone both ways. So what I'm going to tell you about is a little bit about how we proved this result last summer and showed that actually there can exist Hamiltonians for which you can actually prove you can prove lower bounds much further than log n. You can prove just regular log n circuit depth lower bounds. And what this says is something about the theoretical existence of robust entanglement at warm temperatures. Here I write room temperature. That's because there's sort of a physics notion of room temperature, which is 20 Kelvin. You should contrast that with your regular notion of room temperature, which is 20 Celsius. Okay, so that's that room temperature. It's the physicist's room temperature. Okay, so it could maybe exist at some reasonable, accessible temperature. Okay, but let me say something more, which is that this proof of NLTS, it's not really a natural Hamiltonian that exists. It's an engineered object. And I mean engineered in the sense that it required a lot of tools, and it's not like a randomized construction. It's something very specific, delicate, and deliberate in how we define the interactions between particles. But this is sort of what you expect from a talk on quantum computation, is that you're sort of doing something unexpected. We're engineering entanglement to have properties that don't physically appear. And the only thing is that instead of engineering with nuts and bolts, it's engineering with notions of error correction and expander graphs, etc. And this turns out to be the first evidence of the entanglement conjectured by much older conjecture in quantum complexity theory called the quantum PCP conjecture, which I think I'm going to describe next, and then I'll come back a little bit to the proof. Okay, so what is this quantum PCP conjecture? Well, so you might know the classical PCP theorem, which says that, whenever you have an interaction between a verifier and a prover, that's just one round. So, you ask the prover a question, and he responds with an answer. You can always turn that in, due to NP completeness, to a simple interaction where you send him a formula, a Boolean formula, and he responds with an answer to the formula. Right? This is the notion of NP completeness. The only problem is that in order to understand the formula, you have to read the entire thing. You have to check every clause of the formula, one after another. And that seems like the only way to check the proof. The PCP theorem says, actually, you don't have to necessarily create formulas that are so brittle. You can actually create formulas that are a little bit more robust, meaning that you can write down formulas so that if you wanted to check its correctness, you'd only have to check a constant number of those clauses. You just check a few different bits. If it satisfies some simple checks, you accept or reject. So you put the onus on actually writing down the solution to this formula in this complex way. There's another analog to this PCP theorem that's equivalent that says it's actually just the other simple way to think about it is it's NP complete to even estimate the satisfiability of a formula. So to estimate what's the maximum number of clauses you can satisfy, even estimating that to some multiplicative error is NP complete. So what's a quantum analog? Well, earlier I suggested to you that there was this QMA complete problem of this thing about local Hamiltonians, and that in fact turns out to be true. That the QMA analog of NP is just this idea that every time you have an interaction where you ask a prover a question and he responds with a quantum state, you can always turn that into a form where you ask him about a local Hamiltonian system and he responds with the ground state of that system. He responds with the lowest energy of that system. And then the verifier, all he has to do is he has to use his quantum computer to measure and check that the state given to him was actually a low energy solution. So the quantum analog is just that it's QMA complete to estimate the ground energy of local Hamiltonians up to a 1% multiplicative error. And this sort of cements this notion that in quantum computing, the local Hamiltonian, this very physically relevant object, is just the quantum analog of a very traditional object from computer science of satisfiability. Okay, so now what I'd like to say is that quantum PCP, this conjecture, that seemingly has nothing to, just says something about hardness of estimating ground energies, actually says something fundamental about robust entanglement. And let's say that. So if this quantum PCP conjecture is true, so it's QMA complete to just estimate the ground energy, just estimate. A prover could get a little lazy, and instead of sending you the ground state, he sends you the low energy state. He says, well, it was hard to estimate the energy, so let me just send you something which is under 1%, right? 0.5%. So he sends you this low energy solution, and that's totally fine, assuming the quantum PCP conjecture. But what if he gets even lazier? So instead of telling you just the low energy state, imagine that this low energy state was actually the output of a short circuit. So there's some circuit C, which if you ran starting with all zeros in your quantum computer, it would output the state V. Well then, instead of just sending you the low energy state, he could just tell you the description of the circuit. He just sends you the description of the circuit. But now that the prover has gotten so lazy, the verifier also can become equally lazy. He no longer has to run with a quantum computer. He can just use a classical device to do everything. And why is that the case? Well, the C was a trivial circuit. It was a really short depth. So in order to verify some properties of it, he didn't have to use his quantum computer. He could just do this all on his laptop. So what happens is that if there was a very short description of the low energy state, then you get some big complexity contradiction. You get that this quantum complexity class equals NP, which is something we widely believe to be false. So the only way to reconcile this is that this statement that a low energy state is the output of a trivial circuit must have been false. So amusingly enough, the quantum PCP conjecture is actually implying the NLTS theorem. So it's implying this fundamental result about robust entanglement. Or another way of thinking about it is this quantum PCP conjecture, which has been open since 2002. The NLTS problem is sort of extracting out the robust entanglement question from the question of computation. So it says, hey, if you want to try to solve the quantum PCP conjecture, you're inherently going to be solving something about robust entanglement, and you're going to be saying something about computation. Well, are either of those parts true on their own? And let's tackle the robust entanglement one, because if we can prove that one's false, then we toss the whole conjecture out. And so this was sort of the computer science reason as to why people came about the NLTS problem. They were sort of interested in understanding, hey, if our expander and mathematical techniques that took that brought us the PCP theorem, if we could convert those into a quantum PCP conjecture, into a quantum PCP theorem, then we would have also said something very interesting about physics. Well, let's see if we can do the physics part first, and then let's see what that says about the quantum PCP conjecture. So this problem sort of is interesting from both computer science and physics for this reason. Okay, rest of the talk, I'll take some questions in a second, but with the rest of the talk, what I'd like to do is I'd like to say a little bit about the proof intuition, how it connects to notions of PCPs and expanders, and then maybe I'll say a little bit about related results and some ideas for future problems. But before I go on, is there any questions I could take? Yes, please.
So why is it that you define the classical regime as order of log n? Because I know for a fact that, for instance, that the Hilbert space of n spins is size 2 to the n. So why not log n? Why log n?
It's because if you have a circuit of log n depth, it's not clear that how to describe the outputs, how to verify that the output state is the low energy state of a Hamiltonian. We don't know a generic algorithm for estimating the energy of a state of that large depth with any local Hamiltonian. So we only know that trivial regime up to log n. The algorithm after that runs in super polynomial time. So that's why. So if the state is of log n depth, the algorithm would take exponential time to simulate the energy. Yeah. Yeah, so under some plausible conjecture, this conjecture called QMA equals versus QCMA, two different notions of quantum analogs of NP, you actually get that even super polynomial depth must be necessary. And I'll say a little bit about that later. But yeah, so there are other conjectures that necessitate even stronger circuit lower bounds. Yeah. Any other questions? Okay, great. So let's move on to the proof intuition for NLTS. And to start off with, what I should say is that, it's not a surprise that error correction comes up. Error correction was a fundamental question, fundamental tool in understanding the classical PCP theorem. So it's not surprising that we see error correction appear here again. In fact, we almost expected to see it. But there's another reason, which is that error correction has been a very rich source of examples of physical systems that exhibit sort of exotic entanglement. The first clear example was Kitaev's toric code, shown on the right, which was the example of sort of a non-trivial topological phase of matter. And furthermore, if you have an error-correcting code, there's a very simple local Hamiltonian that corresponds to it. You take the parity checks of the error-correcting code, and you just say there's a Hamiltonian term that corresponds to each of them. And what you get then is that the code space, the solutions of the error-correcting code, turn to be the ground space of the Hamiltonian. And you can do this for even a classical error-correcting code, but you can also do this for quantum error correction. And furthermore, error-correcting codes are really good candidates for NLTS because there's a simple argument, relatively simple argument, that proves that the code states, the ground states, are non-trivial. And then the whole goal is to sort of take that argument and make it robust to low energy perturbations. Okay, so let's just say a little bit more on quantum error correcting code. So what is a quantum error correcting code? It's the idea that you take a k-qubit state and you encode it in this larger n-qubit code word. So you take, there's sort of this 2 to the k dimensional space within this larger 2 to the n dimensional space. And it has the property that if a d qubits are erased, you just lose the value there, then you can always recover. There's some recovery function you can apply, and you can get back the code word. And then once you've applied the recovery map, you can decode it to get back to the original k-qubit word. And the code space is just the linear combination of any of these solutions. So it's just you apply the encoding map to any k-qubit state, and the resulting span is the code space. Okay. There's a nice question you can ask about code words that at first seems unrelated, which is, what is the minimum depth circuit that distinguishes two orthogonal code words? So, if you have a code word, let's say you have two orthogonal states that were encoded in code words, so you get this yellow state and this green state. What is the depth of a circuit that outputs 0 on one and 1 on the other? Just distinguishes the two. And it should distinguish, say, with near certainty. Well, there's a folklore theorem, which you can prove, that shows that any distinguishing circuit must have depth at least log d, where d is the distance of the code. I'll give a little intuition on this in a second, but let's notice that this actually implies that code words require circuits of depth log d to generate. That's the case because if there was a short generating circuit, it also yields a distinguishing circuit between the states. So distinguishing is also a prerequisite for the depth of generation. Okay, so this gives you sort of this interesting phenomenon that's fundamentally quantum. Because classically, you could have a simple error correcting code, which is just the repetition code, which 0 encodes in all zeros and 1 encodes in all ones. But you can distinguish these two states by just looking at any one bit, right? They just differ everywhere. Whereas what I'm saying is this red theorem in the top right, that any distinguishing circuit must require log d depth. It can't be such a short depth. Okay, what does that mean? Well, it means that, if the distinguishing circuit has depth d, that means it can look at most 2 to the t different initial qubits. So if there was some output qubit which outputted 1 or 0, then what it is based off of is only 2 to the t of the input qubits, this distinguishing circuit. And this is just because there's an information propagation bottleneck that occurs. So you can rephrase this result to saying any distinguishing circuit must depend on at least d plus 1 of the qubits, where d is the code distance. And this turns out to be a fundamental result that's just truly quantum, but it's actually now proving a complexity of the ground states of a code. On the interest of time, let me not go into why this is the case. All I'll say is that it follows from a very fundamental quantum postulate called the no-cloning theorem. So if you have the no-cloning theorem, plus just the fact that you're a quantum error correcting code, you actually get this local indistinguishability, that quantum states cannot be distinguished without d plus 1 qubits. Okay. So what we have is that quantum error correction implies a notion of local indistinguishability, which implies a notion of circuit lower bounds. And this tells you that ground states of error correcting codes have circuit depth lower bounds, but remember, the whole goal was not to talk just about the ground states. That was already known by Kitaev's QMA hardness. It was to talk about the low energy states. We wanted to prove complexity of low energy states. So to do that, we have to take this idea, this local indistinguishability argument for error correcting codes, which was a very brittle notion, and makes it robust. So let me say a little bit what I mean by that. So let's say two states psi and psi prime are locally indistinguishable. If it takes like d plus 1 qubits, you have to look at d plus 1 qubits of them to distinguish the two of them. They look similar in any smaller subset. Well, that's certainly the case for two code words, psi and psi prime, like I suggested. But what we really want to say is that all the code words around psi also have some fundamental property. That's because we need to prove lower bounds not just about the complexity of psi, but also all the low energy states. And certainly all the small perturbations of psi are low energy states. So you fundamentally need a technique that is robust to some sort of constant size perturbations. And what we found through like a sequence of results, I was a part of this, is that if you take fundamental code properties, such as having high distance and having high rate and expansion, and you combine that with these notions of local indistinguishability and notions of uncertainty, like sort of fundamental quantum postulates, you actually can prove these robust circuit lower bounds. And this comes at the foothills of sort of an emergence of many big ideas in error correction. So in 2021, there were sort of 3 big results. One on classical error correction, proving that there was this construction of constant rate, constant distance, and constant local testability codes, these so-called C-cubed codes. And this was a very amazing construction. It was sort of a breakthrough. And then a month later, there was an independent construction by Panteleva-Kalichev that was about linear rate and linear distance quantum codes, and simultaneously an analogous construction of classical C-cubed codes, sort of cementing this connection between classical codes and quantum codes. This was again simplified by Leverrier and Seymour. The only problem was that none of these results said anything about NLTS, because we didn't know how to take these results about quantum error correcting codes or even classical LTCs and convert them into statements about robustness. What we did in 2022 is we actually said that you can take, if you have this idea of expansion underlying the error correcting code, that when combined with linear rate and linear distance was enough for NLTS. And then we went about proving that one of these constructions, the Leverrier-Seymour construction, has the necessary expansion underlying in order to be NLTS. And in current work that's unpublished, we are trying to show that you actually can remove this expansion assumption, that in fact just having linear rate and linear distance is enough, that the expansion is not necessary, but that linear rate and linear distance necessitates a property we call clustering, which is actually the fundamental property of that you need for NLTS. So let me say, what does this say in a more broad scheme about description complexity? Well, this was about how hard it was to classically describe quantum states, but it was, it was cheating a little bit. And that was because we only proved circuit depth lower bounds. Well, and that was, and hopefully I sort of convinced you that that was reasonable because there was this connection between complexity of states and description length that, sort of gave us this notion of verifiability. But what we really want to do is, prove lower bounds on the lengths of classical descriptions. And if you sort of step back a little and try to prove about just classical descriptions, there's actually a lot more one can say. So what I'd like to do is I'd like to say a little bit about 2 results. One about an oracle separation between 2 complexity classes, QCMA and QMA, which proves that there exists some small generalization of local Hamiltonians under which you can prove even super polynomial lower bounds on the size of classical proofs and circuit depth. And I'd like to say something about quantum search to decision and how quantum search and quantum decision behave slightly differently. Okay, so in order to do that, I have to say something about classical proofs for quantum statements. And so, I sort of suggested 2 quantum classes, one QMA and one NP. And the fundamental difference was that QMA, the quantum prover sends a quantum state to a verifier, and that verifier is a quantum computer, and it interprets the state. And the complete problem here was the local Hamiltonian. The other is NP, where, the prover just sends some classical string, and the verifier runs in classical. Well, there's an intermediate class called QCMA that sits well between these two, where the prover sends a classical description, so that could be like a circuit describing the state, and the verifier is allowed to be a quantum computer. And what you get actually is that if QMA and QCMA are different, then you get this strong result that we want, that ground states do not have polynomial size verifiable classical descriptions, and in particular it proves that ground states cannot be described by polynomial depth circuits. So if you prove a separation between these 2 complexity classes, you actually prove a really strong lower bound. on the complexity of states. Only problem is that proving this sort of separation is very hard. All these classes sit between P and P space, so we don't expect to be able to do that. So, this is sort of like saying it's much easier to just send this description of the quantum state. Any classical description would be too large. The way we sort of do this is we prove this in an oracle model. So we prove that there's some generalization of local Hamiltonians. We sort of massage the notion of local Hamiltonians enough till we can actually rigorously prove this. And what that generalization is if you're familiar with, it's a distribution testing oracle. So in some complexity theoretic scheme, we can actually prove much, much stronger lower bounds than just the NLTS, but it's not an unconditional statement. It requires this oracle separation. The best unconditional lower bounds we have on quantum states is the NLTS result. This might be the best conditional bound on circuit complexity. Okay, last thing I'd like to say is that, all this was about the description of quantum states, but somehow all the complexity questions are all about, the ground energy. So we could ask a question of, how hard is it to generate ground states if we knew how to calculate ground energy? So it's this question of eigenvectors versus eigenvalues. Which one's easier, which one's harder? And in classical computer science, they're actually the same. We have that NP has this notion of search to decision reductions. So, and this is because there's sort of this Boolean hypercube, and in classical computer science, you can sort of binary search over that. The only problem is that it's not possible to binary search over a high-dimensional sphere. This is sort of because of where the mass on high-dimensional spaces sit. So you could ask, hey, is that the real bottleneck? Or can we fundamentally prove that finding a ground state is harder than calculating the ground energy? And the answer is a little bit unclear. There's one result you can show, which is actually you can reduce it to a decision problem, but that problem is much harder. It's some counting problem. And there's another, which is that ground state generation is not reducible, and this is another oracle separation. And it's actually the same oracle separation that is done for QMA versus QCMA. It actually proves something about describing ground states versus computing ground energies. And what this suggests is that more broadly, you can't really understand the complexity of quantum problems through the classical pantheon of complexity theory. You sort of need new tools and definitions to understand the complexity of states. So what I'd like to say is, some future problems that this invokes. And, the first future problem you could naturally say is, well, we should prove this quantum PCP conjecture. There are many reasons why. One, it's arguably one of the biggest open questions. But second, classical PCPs were fundamentally revolutionary. They changed how we look at both cryptography and approximation algorithms. So it stands to reason that if we were able to understand the quantum PCP conjecture, we could actually say something a little bit about the quantum analogs of these problems as well. And it helps us understand the nature of many-body entanglement, right? NLTS was part of the answer. It describes robustness in this one specific circuit lower bound model. But really, we'd like to prove complexity lower bounds against all classical descriptions. That's what's promised by quantum PCP. So if we were able to prove that, it would be sort of the real, creme de la creme of robust entanglement that we could generate. So it seems fundamentally interesting from a physics perspective as well. And then more broadly, we have to think about complexity of states. And these states, they wear so many different hats in computer science that we need to understand how to think about describing them, generating them, manipulating them. And my previous results suggest that, it's not really clear how to connect that to classical complexity theory. And, I'm not the only person who's worked on this. There's been many other results that connect these to notions of preparation and interaction, et cetera. So what I'm proposing is that we sort of need to create a clear definition of quantum inputs and quantum outputs and the complexity thereof. There's a complexity that's defined by quantum mechanics, not just one that's adding quantum to the classical definitions, sort of a redefinition. And in this goal, the goal is to understand notions of reductions and hardness of approximation and interactive proofs. You can start to try to write down things, but any definition you might try seems to, miss something here or there. So is there a clean understanding of what that is? That's a very nice, open, broad question that it's not going to be resolved in any one paper. It's sort of something that is going to take a little bit to understand. Okay, so with that, I'll end with this slide and take any questions.
Do you have any questions?
Rahul?
You talked about, have you thought about spatially local Hamiltonians instead of just scale local? So do you think that the NLTS sort of conjecture holds even if you restrict yourself to like spatially local Hamiltonians or something like this?
So the NLTS result does not hold for spatially local Hamiltonians. There's always like a n to the 1 over epsilon size classical description for any epsilon. But that doesn't suggest that your question is like just wrong. It in fact suggests that sort of there should be an analogous question for spatially local Hamiltonians, like NLTS, that is the right question. And that could be something about maybe the complexity of Gibbs states, thermal states, or it could be something about running classical descriptions that were much shorter than n to the 1 over epsilon. Like say they were like n to the log 1 over epsilon. Right? Understand, like n to the 1 over epsilon is tractable in like a theoretical CS language, but in practice at epsilon equals 1 over 100, that's intractable. So maybe there's a better fine-grained notion of complexity for that specific model that's worth asking about. Yeah.
And also, I was wondering, so I guess coming more from a physics perspective, that so in many condensed matter systems, like there is this belief, at least, that most physical systems have gaps between the first and the ground state and first excited state that at most manage polynomially with n or their gap. So maybe I didn't quite understand what would be the implication of your result. Does it say anything about these kind of problems as well?
Right. So the NLTS, the Hamiltonians we write are gapped.
They're gapped.
They are gapped. Yeah, so they consist of n Hamiltonian terms, order n Hamiltonian terms, and the gap is 1 compared to them. So it's gapped in that sense. It scales inversely polynomially with the number of terms. Yeah, so it is about gap systems.
Okay, I see.
Maybe I have a question, actually. So is there a natural strengthening of NLTS? Like, you consider this circuit complexity. Is there maybe a notion that is, directly quantifying entanglement? Some natural notion that would make sense?
Yeah, so these are all about like NP notions of entanglement, classical descriptions of entanglement, right? And in fact, circuit depth is not the only thing, because there's this whole class of circuits which can be very deep, but can also still be classically described, these Clifford circuits, right? So there's notions of like circuit depth for Clifford plus few T gates. There's notions of you apply a Clifford circuit, then rotate by a stabilizer state. It's actually frankly unclear whether there's some like general notion of classically describable quantum state, some like, truly general notion. That would be fundamentally interesting to understand, but we don't know. We don't know if we don't know if a classical state system that captures the complexity of all classical states. That would be like a notion of reduction, right, between states. We don't know that. That's one of the things we should try to understand. Yeah.
Okay, good. Let's thank Chinmay again for the great talk.